Morning, everybody. Here we have the start of aldehydes and ketones. In our class, it's test 3 in org 2. But the difference between an aldehyde and a ketone is, remember, an aldehyde has a hydrogen on the carbonyl, whereas a ketone has 2 alkyl groups on it. And the carbonyl, as we talk about it, is just a CO double bond with whatever off of it, depending on the functional group: aldehyde, ketone, ester, amide, acid. Okay, so to name an aldehyde, we need to identify and name the parent chain, identify and name all the substituents on that parent chain, number the parent chain so that every substituent gets the right number, the lowest number possible, assemble the substituents alphabetically, and then the last step is to add al at the end of the parent chain for the aldehyde, and then put it all together with any chiral centers we might have in the molecule. Okay. And the main difference between these two is an aldehyde, we use al; a ketone, we use -one in the name. Okay, so remember that the importance of how we name it, and spelling is very important in how we do things. Okay, so can we draw an aldehyde for each of the following compounds? So lithium aluminum tri-T-butoxyhydride, sorry, wrong pen, is a reducing agent because it has that hydride. So all it's going to do is reduce the acid chloride down to the aldehyde, adding a H- to the carbonyl carbon. Diol is another reducing agent. It's going to reduce the ester down to the aldehyde. It also reduces the cyano group down to the aldehyde because we add an H- to the CN triple bond. B2H6 or R2BH, whatever borane you're going to see it as, might be a dicyanal. What's off the boron other than the hydrogen doesn't really matter. It puts the carbonyl at the end of the chain. PCC, or Swern oxidation, remember we learned was an oxidant that takes an alcohol up to the aldehyde. And ozone, we learned back in org 1 that it cleaves a carbon-carbon double bond and creates aldehydes and ketones with zinc and water, or ketones and acids with the hydrogen peroxide. So of these, the first 3 are new, the bottom 3 are old reactions from org 1 and early in org 2. The next page we have draw the ketones. So, and we'll draw mechanisms for a lot of these as we're going along. We're going to add a methyl to the carbon of the nitrile. So we're going to go from 4 carbons to 5 carbons and have a ketone. Mercury sulfate is just like the mercury reagent in org 1, where we put the oxygen on the more substituted carbon. We're breaking 2 carbon-carbon bonds, so we need to get 2 carbon-oxygen bonds. Chromic acid gives us the ketone. The cuprate and the acid chloride, 2, 3, 4, 5, 6. We have to be careful. How many carbons do we have? We need to draw it correctly. So we have the 2 carbons of our acid chloride, and we add 6 carbons on from the cuprate. So we're going to get the 8 carbon ketone. And then the last one we learned in org 1, acid or ozone and a double bond completely cleaves, giving ketones or aldehydes with dimethyl sulfide or zinc and water, and ketones and acids with peroxide. So which is more reactive, a ketone or an aldehyde? The aldehyde is more reactive because if we draw a resonance structure for a generic carbonyl, the one resonance structure puts a positive charge on the carbon of the carbonyl. So what's going to stabilize the cation better? An R group of a ketone or an H of a hydrogen. We remember from Org 1, Chapter 4 in our textbook that the hydrogen only has 2 electrons around it, whereas the R group has 8. So the R group stabilizes cations better than a hydrogen. More substituted cations are more stable than the less substituted ones. So a ketone is going to be more stable than the aldehyde. So the aldehyde would be more reactive under the reaction conditions than the ketone. So can we draw a resonance structure again? Yes, we can. Break the double bond, send it to the oxygen. The hybridization of that central carbon is sp2 because on this carbon there's the double bond of the oxygen, that counts as one, the methyl, and the other methyl. So it's sp2 hybridized with the leftover p orbital on the carbon and on the oxygen, making the pi bond. Where would a nucleophile add to the carbonyl? And the only place it can add is where you have the cation, the central carbon, because remember the charge on a nucleophile is negative. The carbonyl has a partial positive on the carbonyl carbon because of electronegativity. So the nucleophile is just going to add to the carbonyl carbon, send the electrons up, and we're going to get this. And it doesn't matter what the nucleophile is, any good nucleophile will add to the carbonyl carbon. And then after we add it in, we need to work it up with acid to protonate the O- to give us the product. If we're in an acidic solution, we cannot have a weak nucleophile add to the carbonyl, so we have to protonate the carbonyl first. So the oxygen goes and grabs a hydrogen off of the acid. Then our neutral nucleophile can add in, break the double bond, and then another equivalent of the nucleophile can come in and grab the extra hydrogen, neutralizing our product to give us the OH and the nucleophile on there. Now this will continue to go on, and it'll add 2 nucleophiles on there in an acidic solution, and we'll draw that mechanism in just a minute. So the first one, we've drawn the mechanism. The nucleophile adds, we get the O-, we get the nucleophile, we get the hydrogen, and then in the second step we go and grab the H+ to give us our product. In the second one, just like what we drew above, we have to protonate the carbonyl first, and in this section acid catalyzed mechanisms are much better than the base catalyzed because they take longer. You have to be very careful about what you draw, in that they are a bunch of proton transfers that have to occur, so you have to be very careful that you draw all the proton transfers. So we get that, and then that's the exact same thing we drew above, but that can continue on. And let me add a page in here, and we'll draw the whole mechanism for it. So what can we do? Can we predict all the products for all of these? This one is just going to give us the OME and the OH, the hemiacetal. The next one is going to give us the acetal with 2 OMEs on it. This one is going to be just like the one above, because it's not going to stop in the middle at the hemiacetal. It's going to keep going all the way to the acetal. The acetal is a carbonyl carbon with 2 bonds to an oxygen, and the carbonyl carbon is an aldehyde, so it goes to the acetal, whereas a ketone goes to the ketal. So if we have a carbonyl and we add some acidic nucleophile, the first thing we do is protonate the carbonyl, just like what we just drew. We're going to go from there and go on. The nucleophile adds to the carbonyl. You break the double bond. That gets us to the OH, the nucleophile H with a positive charge, because the nucleophile was neutral when it added, so since it still has the hydrogen on there, we have to have the positive on there. A second equivalent of the nuke H will come grab that off. And you have this. Then our acidic nucleophile with two hydrogens on it and a positive charge, the OH can come grab the extra hydrogen off of it to make the OH2 plus and our nucleophile and our H. The nucleophile always has lone pairs on it, so at this point the nucleophile lone pair can go down to kick out the leaving group, so we form a double bond kicking out the water leaving group, and we get this with a positive charge on the nucleophile. Now remember what chapter we're in. We're in the chapter on ketones and aldehydes, carbonyls. So all of these reactions are going to go through a carbonyl equivalent, a carbon double bond to a more electronegative atom. Then we can have a nuke H add in to this, breaking that double bond, and we get a positive nuke H on the carbon of the carbonyl, the neutral nucleophile that we previously added, and then all we have to do is remove the extra hydrogen off of the nuke H to give us where we add two of the nucleophiles under acidic conditions to the carbonyl carbon. It can be an oxygen, it can be a sulfur, doesn't matter what it is, as long as you're in acidic conditions and you have a decent nucleophile, you can do this type of thing. So here's some more. Can we predict the products of all of these? In the first one, it's going to be just like the hemiacetal. We're going to make the hydrate. The zinc, mercury, HCl, we did that previously. That's going to just make the alkane, reduce the carbonyl all the way down to the alkane. The next one is going to be just like the acetal, but it's sulfur instead of oxygen, so it's going to make the dithiene, and then rainy nickel and hydrogen gas reduces that down to an alkane. So it's another way to do a reduction. The first one, zinc, mercury, and HCl, is a strong acid. Rainy nickel and hydrogen gas is a neutral way to do it, and then the next one, the hydrazine and hydroxide, is a very acidic or very basic way to do the reduction to give us the alkane. So those are our three ways to form an alkane in this section. Okay, depending on, do we need an acid catalyzed, base catalyzed, or a neutral way to do it. CN minus is going to give us the OH and the CN. The next one is a Wittig salt, or Wittig reaction. We're going to take the hydrogen off of the acidic carbon, the one next to the positively charged phosphorus, because we can draw a resonance structure of that, and then that's going to react with the carbonyl. We'll draw the mechanism later when it fits on a page. And all we do with this is replace the carbon-oxygen double bond with the carbons off of the phosphorus. So we form an alkene, taking the oxygen out of the picture, replacing it with two bonds to the carbon that were on the phosphorus. The Grignard, we've already done it. It's going to give us the alcohol. Since we're starting with an aldehyde, we're going to get the secondary alcohol. If we started with a ketone, we'd get the tertiary alcohol. Goes all the way back to org, the first test in org 2. The chromic acid is an oxidant. It takes an aldehyde up to the carboxylic acid. And then the last one of these is the peracid. It takes a ketone and forms an ester out of it. So how do we go about drawing all of these neat little mechanisms? So, and remember, the acid catalyzed ones are the better ones to ask, just because you have to be careful about all of the proton transfers. So the hydrate formation, we add acidic water, and it could be acidic water or hydroxide. We can get to it the same way because we don't need to get rid of the oxygen on there. If we have base, it adds in, you break the double bond O, you get the O minus, and then we protonate that, and we're done, where the nucleophile would be hydroxide. If we're an acid, it would be H3O plus, so our nucleophile would be water that would add in, and we would remove the extra hydrogen. But notice that in the acid catalyzed conditions, we have to protonate first, so it is a longer mechanism than if we didn't. So can we draw the mechanism here of the formation of the acetal or ketal? And this one, if the R groups are both alkyl groups, this would be a ketal because it was formed from a ketone. So the first thing we need to do is protonate the carbonyl. And then our alcohol can add in, break the carbon oxygen double bond, giving us the OH, the OR with the extra hydrogen on it, and our other alkyl group. Then our alcohol solution can grab the extra hydrogen off to give us the OH and OR on there, the hemiacetal. Then we can protonate the OH from our acid solution to give us a good leaving group, positive charge, OR, and then the oxygen can send the electrons down, kicking off the leaving group water to go through the carbonyl equivalent, and then your ROH solvent can add in, break the double bond, and we get this where we have the extra hydrogen on the oxygen, and then all we have to do is remove the extra hydrogen, and we are to our ketal. Okay. And here we have it drawn nice and neat, as opposed to my handwriting. I know it's not very good, but here it is. We protonate, we add it in, we deprotonate, we protonate something else, we kick something out, we add something in, we deprotonate. So we have a proton transfer, a proton transfer, a proton transfer, and a proton transfer in that mechanism. So we have a lot of proton transfers that we have to draw. We have to be very careful that we draw all of the proton transfers. Don't leave any of them out. Show all the arrows for those proton transfers. It's just not minus H plus H. Okay, that's not showing anything. That's not very helpful. Get all of the arrows in for the movement of the electron. And as you're doing this, be careful that you never in this section do an SN2 mechanism on the carbonyl carbon. Okay, that is not possible. You have to form the carbonyl equivalent, kicking out the leaving group, and then add it in. Okay, do not do this. I will write a big -5 or 10 on your test and go on from there, because you're not being careful about what can happen in this. Okay, and SN2 can't happen here, so don't try that. An acetyl group can be removed as easily as it can be put on, chalet. If we use excess alcohol, we can force it to go to the acetal or ketal. If we use extra water and acid, we're going to cleave it to go back to the carbonyl. If we wanted to carry out the following multi-step synthesis, and when I say multi-step synthesis, it is not one step. Okay, there's many 2 or 3 or 4 steps that are going to have to go into this, so don't try to shorten it down to one thing. That's not going to be right. Okay, so we can't just add LAH to reduce the ester, because it would reduce both carbonyls. So we have to think about how can we reduce just the ester by keeping the carbonyl, the ketone, around. So how would we go about doing this? The first thing we'd have to do is protect the ketone so we don't do anything to it. So we'd make the ketal with methanol, ethylene glycol, some alcohol, and acid, depending on what acetal or ketal we wanted to make. Okay, the ethylene glycol is a great alcohol to use. And then once we have the ketal formed, after making the ethylene glycol and acid, we can reduce the ester followed by acid to protonate the O- of the reduction from LAH, and to cleave off the ethylene glycol ketal. Okay, so we have to be careful that we go about it in all of the steps needed, and don't shorten anything down as we're going along. So stable hemiacetals sometimes are possible. Most of the time the hemiacetal or hemiketal is not stable and continues on, either with addition of more alcohol and acid, or removal of with water, depending on your conditions of the reaction. The ones that are most stable are like this, where we have a cyclic hemiacetal, where we can protonate the carbonyl, the OH can add in, forming the ring, just like what we have with all of the sugars, glucose, and different sized rings, sugars that are naturally found. We have on this carbon right here a hemiacetal. It's a cyclic one, and glucose, all of the OHs except the anomeric one on the hemiacetal are all off of the ring in the equatorial position, so they're the most stable groups off of it. Okay, so what else can we add to a carbonyl? We can add a nitrogen. So in the previous, with the oxygen, ethanol, methanol, ethylene glycol, whatever we added, we protonated the carbonyl first and then added it in. Here we need a little acid. We have to be careful how much acid we have. We can't use a lot like we did in the previous one, but we have to use enough to protonate the carbonyl. And then once we protonate the carbonyl, we can add our methylamine into it to break the CO double bond, and then deprotonate the nucleophile, just like we've done before. Protonate our OH, and then use the electrons on the nitrogen to kick out the OH to give us the carbon-nitrogen double bond with a positive charge. And then the nitrogen, the nice thing about nitrogen is it can have 3 bonds. So with that hydrogen on it, we can remove that hydrogen from with the amine we have in solution to make the carbon-nitrogen double bond. Okay, so we can make the imine here having the extra hydrogens on the methylamine. Having just the primary amine gets us to the imine. Okay, now I'm going to erase all my arrows so you can see it in all its neatness. Okay, and it's the same basic mechanism we drew with the methanol, ethanol, whatever before, except for here at the last little bit, we added, instead of adding another nitrogen in, we removed a hydrogen. So we got the imine in this one instead of having two single bonded nitrogens off of it. And the conditions for this reaction are very important. It must be mildly acidic. If it's too acidic, all we'll do is protonate all of our amine, and all we'll have is the ammonium salt in solution, and that can't do anything. Okay, so we have to be careful what conditions we do the reaction on. If we have a secondary amine in this, we go to an enamine. Ene because of the carbon double bond, and amine because we have the nitrogen off of it. So in this one, we protonate the carbonyl, nitrogen adds in just like before to give us the nitrogen on the same carbon. The nitrogen has the extra hydrogen on it, so we have to remove it to get to here where we have the OH and the dimethylamine on the same carbon. And then we protonate the OH and we can kick it out, and we have the aminium ion just like we did on the previous one. But on this aminium ion, we cannot remove, we don't have a hydrogen on it to remove. All we have are the methyls. So the only way we can neutralize the aminium ion is to remove a hydrogen off of the carbon that was the alpha carbon to the carbonyl to get us to the enamine. So we grab the hydrogen off of the alpha carbon, send the electrons down to form the double bond, and send the electrons up to the nitrogen to form the enamine. Okay. So as you're going along working problems, look for the similarities in all these reactions. There's a lot of similarities in here. H and so it's not that you have to do everything differently every time. Okay, the Wolff-Kishner reduction, we showed the product earlier of this reduction, but in with KOH and hydrazine, what we do is first we're going to remove a hydrogen off of the hydrazine with our hydroxide. Pardon me, not big enough. So we make the hydrazine nucleophilic by taking a hydrogen off of it. It can then add into our carbonyl to give us the O- and the nitrogen NH2 hydrogen. That O- needs to grab a hydrogen and take one off of the water we just formed off of a hydrazine. Reform a negative charge on our hydroxide. So we get here. From here, since we're in base, we can't protonate the OH again to make it a good leaving group, but we can remove the hydrogen off of the hydrazine to go back to a negative charge. So we have the OH, the N- NH2. Better draw that different. Too close together. Sorry. So we have our hydroxide that grabs that hydrogen off of the nitrogen of the hydrazine. That gives us an OH, an N with a negative charge, and an NH2. Now from this, we have a leaving group. We can go through that carbonyl equivalent of a double bond to a more electronegative atom, kicking out the hydroxide, and we get to a double bond to the nitrogen, single bond to the NH2, okay, the neutral hydrazone that we showed up above. Now from here, we can remove a hydrogen off of that hydrazone to get to the negatively charged. We can draw a resonance structure for this, sending electrons from the nitrogen down to form a double bond, sending electrons from the double bond to the carbon, and we get a nitrogen double bond. We have one hydrogen off of it and a negative charge on our carbon. That carbon there, we can go protonate off of a water, and that gives us the product I'm going to draw on the next page. So I'm going to let this sit here for a second. You can look at it, and I'm going to get ready to switch pages and draw this product from this protonation, and then we'll continue on with the mechanism. So we get this when we protonate it. Now we're still in hydroxide, so the hydroxide can grab the hydrogen off of the nitrogen on the end. That can give us the N minus. Now this, we can't draw a resonance structure for this, but we can send the electrons from the lone pair on the nitrogen, the negatively charged lone pair, send them down to form a triple bond, and we can break the bond to the carbon, sending the electrons to the carbon to give us the carbanion with a hydrogen on it. Now this can grab a hydrogen off of water, off of the hydrazine, off of whatever it runs into to give us the cyclohexane. Okay, and the neat part about this mechanism is how it all is a bunch of proton transfers, and with those proton transfers and the giving off of the nitrogen gas, we can reduce the carbonyl down to the alkane to do something else with it later on. So what all can we do with these? We can take a ketone or an aldehyde. We can make the acetal or ketal. We can make the imine. We can make the enamine, and from those we can cleave those back to the carbonyl. So we have a lot of things we can do. The acetal or ketal is basically a way to, this one here, it's a protecting group. It's going to make it so we can't do anything to the carbonyl. The imine, we can add a nucleophile to easily. We can do different things to it. The enamine is one that it gives us the ability to alkylate on the alpha carbon, because we can send the electrons from the nitrogen down and then break the double bond to send the electrons over to the carbon. So that negative charge there can go out and attack an electrophile, alkylating that carbon, giving us a chance to grow the carbon framework. So the sulfur nucleophile is just like all the others. Okay, R2SH2 plus, we have to have an acidic solution, but we protonate the carbonyl, sulfur adds in, protonate the water, protonate the oxygen to make water, kick it out, add the other sulfur in, and we get to the thing like this, just like we did before. Okay, you should be able to draw this mechanism. We'll go back. So then we can take that dithiene and reduce it down to the alkane with Raney nickel and hydrogen. And no, there is no mechanism for that. It's just the Raney nickel ends up pulling the sulfur out of the compound, replacing it with hydrogens. Now we remember LAH and sodium borohydride from test 1. We can take the ketone or an aldehyde and reduce it down to the alcohol with whatever reducing agent. Lithium aluminum hydride, remember, is the aluminum has 4 hydrogens on it, so there's a negative charge on the aluminum, but as one of the hydrides leaves, it takes the extra electrons with it, making the aluminum neutral, and it transfers to the carbonyl carbon, sending the electrons up. Because remember, where does anything add to the carbonyl? It always adds to the carbonyl carbon. And then the hydrogen on the oxygen is going to come from your acid workup or from the water workup in the second step of this. Okay. But it's just the refresher from what we did on test 1 with the reduction of ketones and aldehydes to alcohols. Page in and draw a mechanism with the formation of the dithiene. So we have to protonate our carbonyl first. Then our sulfur adds in, and it doesn't have to be in the 1,2 on the ethane. It could be CH3SH. It could be an ethyl. Doesn't matter what it is. We just have to be consistent with what we're doing with it. So this gives us the OH, the SH. Then we remove the extra hydrogen. To give us OH, the SH. Now we have to protonate the OH to make it a good leaving group. So we're going to remove one of the extra hydrogens off of the sulfur. That's going to give us the OH2 plus along with the SH. Now the sulfur has the lone pair, just like the nitrogen and the oxygen, so we can use it to kick off the leaving group water. Add it in, break the double bond, sending the electrons up to the sulfur. So that gets us to the sulfur, 2 carbons in between with a hydrogen on one of them, the one that was out on the end. Can be drawn either way with either of the sulfurs with a positive charge, as long as you're consistent with how you go about doing it. And then we could have our water come in and grab the extra hydrogen off of it to give us the dithiene. Okay, and that's what we'd put into the mechanism. It's the same mechanism as oxygen, exactly the same, because remember where sulfur is compared to oxygen on the periodic table. Okay, right below it. So they're going to react the same. The only difference is the sulfur is a little more acidic than the oxygen, but they're going to do all roughly the same things. And here's the mechanism again. The lithium aluminum hydride kicks a H minus, a hydride, off to add to the carbonyl, and then the carbonyl oxygen, when it has L minus, goes and grabs a hydrogen off water to give us the alcohol. We did the Grignard reagent. It's much the same thing. Remember the Grignard, the easy way to think about it, it's not completely ionic, but you can think about it as an R minus and an MgBr plus. And the R minus adds to the carbonyl, breaking the double bond, and then you protonate the O minus with your acid solution in the end. Okay. just like the reaction some of you have done in lab with the phenylmagnesium bromide and benzophenone to make the triphenylmethanol. So, but it's just the nucleophile adds. You don't have a way to get rid of the oxygen, so we still have the oxygen on the carbonyl there. We need the acidic conditions to get rid of that oxygen. The cyanide is much the same way. Okay, the nucleophile, the cyano group, adds to the carbonyl, break the CO double bond, and then you protonate it to get the cyanohydrin. It's the exact same mechanism as the Grignard, as the LAH. They're all basic catalyzed mechanisms, so you still have the OH on there. It's just, what did you add to the carbonyl carbon? Once we have a cyanohydrin, and we can either reduce the cyanide down to the amine, so the carbon of the cyanide ends up accepting the two hydrogens off of the LAH to reduce it down to the primary amine, or we can cleave the H3O plus with acid, with acidic water, cleave the cyanide to the carboxylic acid. We still have, remember, the cyanide, if we draw this out, the cyanohydrin. The cyanide is a triple bond to nitrogen, 3 bonds to that more electronegative atom. So unless we have a reducing agent around, we're going to keep 3 bonds to a more electronegative atom off of it. So with acidic water, we go from 3 bonds to nitrogen to 3 bonds to oxygen. And we'll draw both of these mechanisms as we're going on when we get past test 3 into test 4 material. The Wittig reagent is shown here. The yelid is resonance stabilized. We can have the negative on the carbon, or we can send it down to form a double bond between the carbon and the phosphorus. In which way you draw it in the mechanism, it doesn't matter. Okay, the Wittig is an efficient way to convert a ketone or an aldehyde to an alkene. A very good way to do that. Whatever is off of the phosphorus, in this case that CH2, replaces our carbonyl oxygen to make the alkene out of it. Okay, and on the next page we'll draw a mechanism for this. So the yelid adds to the carbonyl carbon, breaking this CO double bond. Then we have the beta-ene here, where the O- and the phosphorus with positive react together to form the 4-membered ring, an oxyphosphatane, and then the oxyphosphatane breaks apart to form the triphenylphosphine oxide, which I didn't draw, and the alkene. And the bonds that have to break are the carbon-phosphorus bond. So when that bond breaks, it's going to break to the more electronegative atom, the atom that has a bigger pull on the electrons, the carbon. And the carbon-oxygen bond, when it breaks, is going to break with the electrons going to the towards the oxygen, because the oxygen is more electronegative. So we end up going from the 4-membered ring, having it split apart and forming 2 double bonds. The PO double bond, when the electrons from the carbon-oxygen bond break, coming towards the oxygen to form the PO bond, and from the PC bond, when it breaks, the carbon is more electronegative, so that one forms the carbon-carbon double bond. So how can we form this? The first step is with triphenylphosphine, we can do an SN2 on any alkyl halide. So we're going to get, well, I should draw the CH3 out. This with an I minus, this gives us the phosphorus with a positive charge, and then the N-butyllithium, or whatever butyllithium we use, N-sec iso T, pulls off a hydrogen off of the carbon attached to the phosphorus, giving us the yelid the negative on the carbon and positive on the phosphorus, and we can draw the resonance structure of that, sending the electrons down to form a double bond. So here it is neatly shown where the phosphorus does an SN2 on the methyl iodide, and then the N-butyl lithium comes in to grab the extra hydrogen to form the yelate. And then that can react with the carbonyl, whatever carbonyl. Now this is, since it takes N-butyl lithium to form, a very reactive species. So you can't have any acidic hydrogens in your molecule if you're going to use the straight Wittig. Now there are ways we can get around this that we'll talk about later, but the straight Wittig can't have any acidic hydrogens in your structure that you're reacting it with. Then we have the Baeyer-Villiger oxidation of aldehydes and ketones, where we take a ketone, oxidize it to make an ester, okay, and from the ketone, if it's acyclic, we get the acyclic ester. If the ketone is cyclic, we get the cyclic ester, or what's known as a lactone in that. And the rates for migration are shown below on the test. If I have a Baeyer-Villiger oxidation, the ketone that I ask you to draw the product from, predict the product from, will be symmetrical on both sides, so you won't have to decide which one migrates better. Okay, but it is here on the bottom of the page what the migration patterns are. So what can we do with all of this? We can convert from a triple bond to a double bond to a single bond, alkyne, alkene, alkane. We can go to an alkyl halide. We can go from the alkene to the alkyl halide. We can go from the alkene to the alcohol, from the alcohol to the alkyl halide. From an alcohol we can make carbonyl, and from the carbonyl we can do all the neat stuff from this section. So most of the previous is stuff from before this section, and here we're just going on from there with what we can do. Okay, so think about these reactions as you're going along. They're very important that you understand what is possible in this, and you see the strategy. So is there a change in the number of carbons? Is there a change in the functional group? The two things you need to think about as you work problems in this section, in this class, as we're going along, as we go towards the end of the semester.